Hi. So today we're going to continue our discussion of the RISC-V processor and how we write assembly language programs that can basically handle anything that we could write in a high-level language program. And so we started last time by going over the basic instructions that are available in a RISC-V processor. And we learned that there are three main types of operations. The first are your computational operations. So this came in one of two forms. Either we had the register-register operations, which take two source registers as their sources, perform the operation in the arithmetic logic unit, and then produce a result that goes back to the register file. Or we have the second form, which is the register immediate, which instead of taking its two sources from two different registers, one of them comes from a register and one is a small constant that's encoded into the instruction. In addition to our computational instructions, we have control flow instructions. And here again, we have two different types of control flow instructions. We have unconditional jumps, which are our jump and link and our jump and link register instructions. And we have our conditional branches, where we're basically taking a comparison between source 1 and source 2. If the comparison returns true, then we branch to label. Otherwise, we just execute the next instruction. And finally, the third type of instructions are loads and stores. And this is what allows us to move data back and forth between the memory and our register file. Okay? And the last thing that we introduced at the very end of last lecture were pseudo instructions. And so hopefully in recitation yesterday you got a chance to see some of the our handout for the instruction set architecture for the RISC-V as we use it in 6004. And there, in addition to listing all the instructions and their encoding formats and things like that, it also lists the definitions of the pseudo instructions that are available to you. And the most common pseudo instructions are things like move, which basically lets you copy something from one register to another. And there's also a couple others which we'll see some examples of in just a minute. So before we move on to new material, I wanted to go over something that I saw some questions about on Piazza, and I feel that confuses students every single semester. So let's go through it a little more clearly. And that's the difference between the registers and the memory and how we make use of them. Okay? And so here's the picture that we saw last time, where I've only shown a subset of our 32 registers, but here we have some registers, and I've given you some initial values for some of them. And then I've shown you a piece of our memory, okay? So just to make sure we're all on the same page, suppose that I'm executing the instruction add x1, x2, x3. Who can tell me, based on this picture, what's going to end up in x1? What is this instruction doing? It's adding the contents of registers x2 and x3. What's in registers x2 and x3? It's two hexadecimal values. So I have 8 and 1 4. So it's a tiny bit confusing. So what does that give me in hex? 1C, right? And so what x1 is going to be set to is 1C, and I would basically, the result of this ALU operation would be that I write the value 1C into register x1, okay? Now, suppose I ran the pseudo instruction move x4, x3. What's going to end up in x4? Yep.
0x14?
Exactly. It's the value that's currently in x3, which is 0x14, and so all I'm doing with that move instruction is I'm copying the value of one register to another. It's simply easier than doing an add with a 0. You can just say move, which will just copy it. All right, so now we get a little bit more confusing, which is with our load and store instructions. So here I have a load x5 0x3 instruction. So first of all, which of these registers is going to be updated? What's my destination register? X5, yes. And what is it going to be updated with, given that I have this instruction that says 0x3 as something about where my data is coming from? So what does that mean? So let me remind you guys. So the way that memory works is that basically we have to give it an address to look up, and then it's going to give us back the data that's at that address. So the address that we're going to look up is computed by taking the contents of X3 and adding 0 to it. So what is that? It's 0x14. Yes, everyone with me? Good. So if I'm doing a load from address 0x14, what is going to end up in X5? What's in memory at location 0x14? 0x23. Okay? So my X5 is going to get the value 0x23. Does everybody see how that's different from a move operation where we're just copying the value of one register to another? When you're doing a load, you're not copying the contents of X3 into X5. Instead, you're using that as the address, looking that location up in memory, and the value that's in memory at that location is what's being put into the register. Is that clear? Great. Okay, so just a couple others before we move on. So suppose I had a similar load instruction, but this time I had an offset of 8. What's going to end up in register X6? 0x16, right? It's just saying, look at location 0x14, go 2 more beyond that, and that's the value that's going to go into register X6. And finally, we'll do a store operation. And so I'm going to store here. Where is the value that I'm going to store coming from in this case? X6, okay? So the store is a little bit different from all of our other instructions in that the first operand is not a destination, it's actually our source, okay? And so we're going to store the contents of X6, which is 0x16. And where are we going to store it? At address what? Our address is computed by adding C to the contents of X3, and so it basically means it's 3 locations beyond the 0x14, and so I'm just going to write 0x1C into that location. Okay? Hopefully that's clarified a little bit for everybody the difference between how we manipulate things via registers and how we use memory. Okay? So just keep that as a little reference guide. All right, so now let's move on to today's topic, which is we're going to, we talked last time a little bit about, how we would translate basic expressions into assembly language, but today we're going to do a more formal definition of how you would translate any higher level, or most, I should say, higher level language programs into assembly. And so we're going to start off by first just reviewing what we do with basic expressions. Okay, so if I want to execute A is equal to B plus 3, and I'm telling you to assume that A is in register X1 and B is in register X2. What's the assembly instruction that will take care of that? Yell it out. Add I, yes, of what? What's my destination? X1, and what am I adding? X2 and 3, right? Okay, terrific. So this is easy because I have my add I instruction, which is the register immediate type of my computational instructions. And it's pretty simple to translate this particular expression. Now, suppose that I give you something similar, except this time my constant is really big. Okay? We can't use add I for this because the constant, as we mentioned, is limited to being only 12 bits wide. By looking at this hexadecimal, remembering that every hexadecimal bit corresponds to 4 bits, this is clearly more than 12 bits long, and so we're not going to be able to use add I for this. So instead, we use a pseudo instruction, which is going to become very handy for you guys, which is called the LI, or load immediate. Now, don't get confused by the fact that it stands for load immediate, because it has nothing to do with memory. Okay, so load immediate is not a load from memory. It's just putting a value into a register, and if I had my way, I would call it something else. But in any case, so load immediate is just putting a constant into a register. And the cool thing about the RISC-V compiler is that load immediate translates this pseudo instruction into 2 different things depending on the size of the constant that you give it. So if you give it a really big constant, then it's going to translate it into these 2 instructions, and I'm going to talk about what this new LUI instruction is in just a second. But if I give it a small constant, like I just want to load the value 0x12 into my register, then it simply translates into a simple add I instruction with the constant being the constant that's passed to the add I. Okay? So now let's take a little bit of a look at these 2 instructions right here. So I lied a little bit last time in that there's actually another instruction that that we use in 6004's RISC-V, which is this load upper immediate. Okay? So what does this do? This basically allows you to take a constant and put it into some register, let's say x1, but what it's going to do is let's say this constant was 0x123, what would end up in x1 is 0x123 with 12 zeros appended to it, or in hexadecimal, 3 zeros appended to it. Okay? So what is this allowing us to do? It's allowing me to take this very big constant and somehow get it into my x4 register by doing a load upper immediate, which is going to put this 123000 into x4, and then I add the bottom 12 bits, which is 4, 5, 6, and now I have this constant 0x123456. Okay? Everyone comfortable with that? Yes?
Does load upper immediate call load immediate for the next one, or does it try to add it immediately?
Sorry, you're talking about this next one here? Or are you talking about up here?
Yeah.
So load upper immediate is actually one of the RISC-V instructions. So the load immediate pseudo instruction, when presented with a large constant, will translate by the compiler into these 2 instructions. So it'll actually execute 2 RISC-V instructions to achieve this. Okay? Any other questions? Yes?
Why is the zeros added to the end of the hex number instead of the beginning? Wouldn't that change the value of the number?
It does change the value, which is actually exactly what we want to do. Okay, so you just want to realize that if you say load upper immediate 0x2, what you're putting into your register is 0x2000. Okay? And so you have to keep that in mind. But the idea is that by doing this, the load upper immediate has a capacity of a constant that's 20 bits wide. So if I use the 20 bits from the load upper immediate, and then I do an add I, which allows me to add the bottom 12 bits, then I'm able to basically represent a full 32-bit number. So this allows me to put any 32-bit value into my register by using those 2 instructions. Yes?
LI is like, I don't know, it can handle big numbers, then when should we use add I?
You can always use LI. Add I is going to be, LI will just translate into add I in all cases where the constant is small. So you should just know that underneath what it's doing is an add I. Okay? Yeah?
So we have like really big constants and we're loading it. Like, doesn't the register also have like? So what if we wanted to store something that was like bigger than the
We can't. Okay, so we're limited to 32 bits. So we could, if we started to do more complicated things like represent a number across 2 registers or something like that, and that would give you 64 bits, but we're not going to get into any of that. Okay, so we'll assume that our data limit is 32 bits. Okay? All right, let's move on. So, so now how do we go about compiling, a complex expression? Well, let's follow these sequence of steps. The first thing I'm going to do is I'm going to take my variables and I'm going to associate some register with each of the variables. Then I'm going to translate my operators into computational instructions. Then I'm going to use register immediate instructions for any case that my expression includes a small constant. And finally, I'll also use the load immediate pseudo instruction if I need to load a large constant. Okay, so let's take this step by step. So we're going to start off translating the x plus 3, and we're going to assume these registers that I've listed here, and I've also given you registers x13 and x14 for some of our intermediate values. All right? So first thing I want to do is compute x plus 3 and put it, let's say, into register x13. How do we do that? Add I, right? So we have an add I instruction that's going to write into x13, and it's adding x10 plus the constant 3. Okay? Next, I'm going to compute the other sub-expression, this y plus this large constant. And so we saw that the way we deal with a large constant is we use a load immediate to load it into a register, and then we add the y, which is in x11, with the temporary value that's in the x14 register to get y plus 1, 2, 3, 4, 5, 6. Okay? Now we need to take those two intermediate results that are in x13 and x14 and OR them together, right? And so I'm going to have an OR instruction that takes the OR of 13 and 14, and this time it's going to put it back into x11 because I want it to be stored in my variable y. Everyone clear with this? Great. So now let's do the next one. So the next one is very similar. I'm going to do x times 4, except the little caveat is we don't have a multiply operation. So how can I achieve x times 4? Anybody remember? I see this, which basically means shifting, right? So I'm going to shift by how many bits to achieve multiplication by 4? 2. Excellent. So I do an SLLI, which is a shift logical, left logical immediate. So I'm shifting x by 2 bits and storing that into this temporary register. And then I take the exclusive OR of that temporary register with y, which is an x11. I store that into x12, which is z. Okay? Everybody comfortable with this? So far, straightforward, right? So now we're going to move on to more complicated expressions. All right? So we saw a little bit of this in the last lecture, which is, suppose we had an if statement. And so an if statement looks like if expression, and then if the expression is true, I execute the body. If the expression is not true, then I want to skip the instructions in the body. Okay? So how do we achieve that in assembly language? We basically follow a very simple recipe, which is what's shown here on the right. So the first thing you're going to do is you're going to use what we just learned in the previous slide for compiling any general expression. Okay? So you're going to compile that expression and put it into some register. Then you're going to check, is this expression true or false? So if it's equal to 0, that means it's false, which means you do not want to execute the if statement. And so if it's equal to 0, which is what EQZ is a pseudo instruction for, then you jump to end if. If it's not equal to 0, that means the condition was true, then we're going to go ahead and actually execute the if statement, which I'm not showing you the details, but basically you would compile all the expressions just as you did the conditional expression. okay? And then when you're done with that, you would basically end up in the end if label as if, you know, it doesn't matter whether you executed the if or you didn't execute the if. In both cases, you'll end up at the end if label. You'll be ready to continue. All right? Good. Okay, so let's try out an example. So suppose I want to do this is x less than y, and if it is, then set y equal to y minus x. So if I follow this recipe directly, this is going to translate into the following. Suppose that x is in register x10, y is in register x11, and what I'm going to do is I'm going to use, for this first time you guys are seeing it in lecture, is this set less than instruction. So what does set less than do? It's going to compare, is x10 less than x11? If it is, it's going to set x12 to 1. Otherwise, it sets it to 0. Okay? So now I can come and check the value of x12. And I'm saying, if it's equal to 0, meaning that the condition was not true, I jump to my end if. Otherwise, I execute my if statement, which in this case happens to be this subtract operation. Any questions about that? Great. Oh, yep.
When you initialize variables like that, does it store them in the register first or in memory first?
So in this case, I didn't really initialize the registers. I'm just telling you to assume that. If you actually were writing a full program, you would first have to initialize your register by bringing a constant or something into the register in the first place. But you don't have to use memory for that. So in other words, if you wanted the initial value of x10 to be 3, you would just say load immediate x10 3 or add I, you know, whatever, with the 0 and 3, and that would get you the x10 initialized. So that doesn't deal with memory at all. But if, on the other hand, well, you know what, we'll get to that later. Okay. All right, so now what I wanted to point out, though, is that it's sometimes possible to make our code a little more efficient by taking this the setting expression, which is doing the comparison, and the branch expression, and turning it into a single expression. And so here what we're doing is we're checking the opposite condition, and we're branching to end if in that case. So this is what we saw in last lecture, where we're saying that if x is greater than or equal to y, then I don't want to do my if, so I'll branch to my end if. Otherwise, I'll do the subtract. Okay? So the two are equivalent. It's just that in one case, on the right here, I only needed 2 instructions, whereas on the left, I needed to execute 3 instructions. All right? Okay. What about if then else? As you can imagine, pretty similar. So here we're going to compile our expression that's in the if statement. If it's equal to 0, you're going to branch to the else. Otherwise, you're going to have the code for the if statement. And then you're going to have this extra instruction which says jump end if. And what is that jump end if doing? It's skipping the else, right? So if I executed the if, I don't want to execute the else, and so I want to jump to the code immediately after it. If I'm executing the else, then I went from here to the else, and then that will be where my else is compiled. All right, so now let's move on to something we haven't seen, which is loops. Okay, so suppose that I have a while loop, which hopefully you guys are all familiar with from your programming experience. And so let's say that I want to say while a particular expression is true, execute this sequence of instructions over and over again. Okay? So I can write that in assembly in the following way. First thing I'm going to do is compile the expression into some register in order to determine if I'm executing my loop at all or not. Right? Then, like with the if statement, I'm going to say BEQZ, meaning if my expression is not true, meaning if it's equal to 0, then I jump to end while, so I don't execute the while. And if it is true, then I have the code for the while statement in here. And now the difference is that this jump is taking me back to the beginning of the while. Okay, so when I do jump while, I'm going to go ahead and repeat that entire set of instructions over again. Okay? Now, there is also, once again, a slightly simpler version, or I don't know if you'd call it simpler, but more efficient version, because if you look at the details here, we have two control instructions. We have both a B, EQZ, and a jump all inside the loop of our while. And those can be a little bit costly, and so it could be more efficient to see if we could rewrite this in a way that only had one control flow instruction. And I'm just going to go ahead and show you how you can do that, which is the following. So what you would do is, instead of starting with the code for the while, you would jump to your comparison as the first thing you do. That's going to tell you, should I execute the while or not? The comparison code is just the expression compiled and then checking, in this case, if it's not equal to 0, meaning is the condition true, in which case I want to execute my loop. So if it's not equal to 0, I come and I execute my loop, and here is the code for my while. And in this case, I don't need another jump, because what I want to do at the end of the while is always check that comparison again in order to see whether I want to repeat the loop or not. Okay? Any questions about that? Great. All right, so let's just do a little example to put all of this together. And so here I have a while loop that has an if statement inside it. All right, so we're going to take this piece by piece. So first what we're going to do is we're going to assume that, again, x is in x10, y is in x11, and we're going to translate the while. So how do I check if x is not equal to y? Anybody? What branch instruction can I use?
Check whether that's 0 or x minus y.
You could do x minus y, but we actually have comparison instructions that just check directly if they're equal, right? So if I ran, if I ran this BNE instruction, which checks is x not equal to y, what do I want to do in that case? In that case, I want to go ahead and execute the loop of the while, okay? So if x is not equal to y, I go ahead and go back to this loop, okay? So first thing I did was I jumped to so we're using the second form of the while loop. I jumped to the compare. The compare checks if I want to execute the while or not. If it does, I go in here and do the loop. Now in here is going to be the compilation of my if statement. Okay, so here I have an if then else. And so again, I'm going to follow my recipe. And this is going to say branch on less than or equal to x10, x11. So if x is less than or equal to y, I'm going to go to my else. Otherwise, I'm going to execute my if, and I'll jump to end if. And then if I jump to else, then I'll do the else, which is y minus x versus x minus y. Everybody follow this? Good. All right. So now, let's go one step further. So suppose that I had this piece of code, and I want to use it over and over again, right? So I want to write a procedure or a function which I might want to call multiple times throughout my program. So how do we go about doing that in assembly? Okay? So here's where things get a little bit more complicated, and the rest of this lecture is going to talk about this. I will warn you that there's a high likelihood we will not finish the entire lecture, which is fine, because we have Tuesday's lecture to finish it. But so I just want to go through it at a speed that everyone can follow. So bear with me. All right, so how do procedures work? Basically, you have a procedure name, you have some arguments, and then you have, the code of what the procedure needs to do. And so, in more detail here, we've got a single entry point, which is the name of our procedure. We've got 0 or more arguments, which in this case are A and B. And we've got potentially some local storage, which is just storing some temporary variables that are internal to the procedure. Okay? And then we also have a return statement, which is going to return the value that this function produces. Okay? So we have to figure out a way to do all of these things in assembly. So in addition, we're going to be able to, once we're able to handle procedures, then we're going to have a lot of power beneath our belts, right? Because then you're able to essentially abstract things away, right? So just like in a high-level language program, if I wanted to write the procedure coprimes, I don't have to write all the code for GCD within coprimes. I can simply call GCD, right? And so we want to be able to achieve the same exact thing in our assembly programs as well. Okay, so what's complicated about this? So what's complicated is that the piece of code that's calling the procedure and the procedure itself are using the same registers, the same 32 registers that this processor has, right? We can't just magically create another 32 of them for the procedure. And so we have to figure out how the calling code is going to interact with the procedure itself. Okay, so the first thing that we're going to hold as a requirement is that the caller can not assume that that the called it's not going to rely on how the called procedure manages its registers. Okay, so it's going to assume that the procedure might overwrite its registers. So if there's some value that it needs to keep upon return from this procedure call, it has to worry about making sure that it kept a copy of it somewhere. Okay? So, and also, ideally, when we write a procedure, right, we'd like our abstraction to be that I don't have to think about everything else that's running in this larger program. Ideally, my procedure should be able to use all of the registers as if it's the only thing running. Okay? So how can we achieve that? The way that we do that is that anytime you make a procedure call, depending on the type of register that you're dealing with, and we'll talk about different types of registers in a minute, it's going to be either the caller's responsibility or the callee's responsibility. So the caller is the one that's calling GCD. The callee is the GCD code itself. And so it'll be one of the two's responsibility to make sure that it saves any registers that need to have their value maintained so that upon completion of the procedure, it can restore those registers, return to the calling procedure, and the calling procedure can continue as if none of its registers were touched. Okay? So that's what we're trying to achieve. All right, so there's a few things we're going to need in order to do this. So the first thing is, we talked about procedures needing arguments. So for arguments, things are pretty easy. We're just going to use registers in RISC-V to pass our arguments. And specifically, we actually have 8 registers we can use to pass arguments. And our return values are also going to be returned in registers. And we have 2 registers that we can use for return values. All right, but now let's talk about this linking thing that we skipped last time. Okay, so suppose that I want to call this procedure, let's call it sum, and I want to call it multiple times from within my program, right? So I might call it here at address 0x100, and I might call it here at address 0x678. By the way, why am I talking about addresses here? Where are our instructions actually stored? Just like our data, they're stored in memory. Okay, so in order to look at our instructions, we actually have to get something from memory and then figure out what it is that it's telling us to do. All right, so this says jump to sum. So ideally, you want it to be the case that, you know, the sum procedure, which at the end of it is going to want to jump back to the instruction immediately following where it was called, should be able to just run the same instruction regardless of where it was called from, right? So how can we achieve that? Right, in one case, I wanted to jump back to address 0x104. In the other case, I wanted to jump back to 67C. So the way that we do that is that we save the return address. So what exactly does that mean? So let's take a look. So this is where our jump and link instruction comes into play, and where we're actually going to make use of this register that's also part of this instruction. So when we make a procedure call, what we're going to do is we're going to do jump and link RA, which stands for return address, comma label. So what is this going to do? This is going to store the address of the instruction immediately following the jump and link instruction into register RA. And then it's going to jump to address label, which is where my sum procedure lives. Okay? So let's take a look here. So I've got my two calls of sum. Let's start with the one at address 100. So the first thing is I'm going to say JAL RA sum. And, sorry, I'm not seeing what this says. Jumps instruction, right, so I said that. Okay, so we start executing this jump and link instruction. The first time we do it, RA is going to be set to 0x104, which is the address of the instruction immediately following this jump and link instruction. Okay? Now I'm going to jump to label sum. So I'm going to go to the piece of code that's at label sum. I'm going to execute all of this procedure basically. And when I'm done, I'm going to say jump register RA. In this case, I'm not trying to save my return value because I'm actually exiting my procedure. And so all this is doing is jumping to the address that's saved in RA. And so that means it's going to come back to this address 104. Okay? So now, after I've completed the procedure, I continue with the instructions that follow that procedure call until I get to the next procedure call. All right? Now, once again, I call jump and link RA sum the same exact way in order to call this procedure again. Except this time, when I call it, what's going to get stored into RA? C, exactly, the return address, which is the address immediately following this call to the sum procedure. Okay, so now I go ahead and execute it again, and when I return this time, I'm jumping back to address 67C. Okay, and so then I jump back, and I can go ahead and continue executing. Any questions about that? All right, good. So, of course, it's not all that simple because we have nested procedure calls, right? So, if I have procedure A calling procedure B, and that procedure calls procedure C, and I just have a single register, this RA register, which is used to store return addresses, I'm going to have a problem. Right? Because when procedure B calls procedure C, it's going to overwrite the return address that I was trying to save for procedure A. So we have to have a way of dealing with this. So the way that we're going to deal with this is as follows. We're basically going to have some storage needs every time we make a procedure call. Specifically, every time you make a procedure call, you're going to need to worry about three things. The first is input arguments. The second is the return address. And the third are the results. And in order to do this, we're going to use local storage for every single procedure call instance, I should say. And so in this local storage, we're going to store both any temporary variables that the procedure wants to use, and we'll also store any registers that we need to save so that we can restore them upon completion of this nested procedure. So all of that together we call an activation record, and we'll see some examples of this in just a minute. Okay, so here's how it looks. So I'm going to make a procedure call. So this is A calling B calling C. And for A, I'm first going to save a bunch of registers. Then when B comes along, I want to make sure that I keep A around. And now I'm also going to, in memory somewhere, store the values that are associated with my procedure B, and so on. And so when I call procedure C, I want to make sure that I can somehow have access to all of these pieces of information. So let's just think about the RA register for a second, right? So suppose that that A calls B. It's going to store the return address, which is somewhere inside A, into RA. And that value is going to be saved in here. Now, if B calls C, it's going to overwrite that RA value, but because we have it saved somewhere in memory, we're able to restore it at a later time. So let's see how that looks. So specifically, we're going to introduce a new data structure, which is what's used in order to implement procedures, which is called the stack. And the way the stack works is in a last in, first out order. So basically, just like this picture shows, the procedure that was called last is above the ones that were called before it in the stack. And we have two types of operations that we can execute on a stack. They're called push and pop. So basically all they are is push puts something onto the stack, and pop takes something off the stack. When you're dealing with a stack, you're basically just dealing with a piece of memory and a pointer to some location in memory, which we're going to save in a special register called the stack pointer. Okay, so when I do a push, it means I'm going to put something new on the stack and make the stack pointer go to the next location. When I do a pop, I do the reverse. I take something off my stack, and now the top of my stack points to this location over here. So let's take a closer look at that. So first of all, it's going to look like this picture that I drew for you here. But let's actually take a closer look at how pushes and pops work. All right? So the way that we have our stack is that it's actually going to be located at the highest addresses of our memory. All right? And so if you look here at this picture, your stack grows from the bottom up, and the addresses here are lower addresses than the addresses here. Okay? So what does that mean? That means that when I do a push operation, I'm going to put some value up into this next available spot in my stack, and my stack pointer, which points to the latest element that I've put on my stack, is going to decrement in value because it's going to be at a lower address. Okay? When I do a pop, I'm doing the reverse. I'm making my stack pointer point to a location lower down, so I'm incrementing my stack pointer, which effectively means that I've taken something off of the stack. Now, I don't actually get rid of it from memory. It's still there, but by the fact that I've moved my stack pointer so it no longer points to that location, I've effectively taken it off my stack, and now I consider this new location that the stack pointer is pointing to as the top of my stack. Any questions about that? This is not simple, so we're going to start working with it, and through some examples, hopefully this will become more clear. Okay, so as I mentioned, the stack pointer points to the last pushed element. So So the key thing about using stacks is that you can use the stack whenever you want. So basically, if you don't have enough space in your 32 registers to save everything you need to work with, then you can use the stack in order to save, to get additional space. But it's your responsibility to return the stack when you're done with your procedure implementation in exactly the same way as you received it. Okay? So let's take a look at how that works. So the first thing that is going to be the responsibility of any procedure, or I can say the callee, is to make sure that it saves any of the registers that it's responsible for saving. Okay? So specifically, in the case of let's assume that I have, a procedure that is going to want to save. We'll talk in a minute about which registers exactly we save, but suppose that I wanted to save registers RA and A0, okay? Then at the top of my procedure, I would basically have these 3 instructions. So what does this do? This first decrements my stack pointer by n. So n is saying I want n locations in my stack in order to save these two values. So as I mentioned, because each one of these values is 32 bits, then it's 4 bytes wide. And so if I wanted to store 2 things on the stack, my instruction would be add I sp minus 8 in this particular example. Okay, now once I've moved my stack pointer up by 8 bytes, now I have 2 empty locations available. So I can store RA and A0 into my stack, and now my stack pointer points over here. Okay? So now I can go ahead and write the code for my procedure, not having to worry about the fact that I might overwrite RA and A0. Okay? And so I'm going to go use all the registers that I want. And then when I'm done executing my procedure, I'm going to have what we call an exit sequence. And so the way that we end each procedure is that we undo what we did in the entry. Okay? So basically I'm restoring the registers that I saved. So I'm restoring register RA from the location pointed to by the stack pointer, which was right here. I'm restoring A0 from SP plus 4, which is this location. And then I increment SP by 8, so now these 2 things are effectively no longer on the stack. And I've restored RA and A0 to their initial values. Does everybody see how we're doing that? Excellent. Okay, so this is where we get to the RISC-V calling convention, which is going to specify whose responsibility it is to save each different type of register. And until now, we've always talked about our registers as if they're all the same. We've said we have registers X0 to X31, and the only one which was special so far, which was X0, whose value was always 0. Okay? But in reality, we actually assign special roles to each of these registers, and that's what we're going to see right now. So the first set of registers are what we call the A0 to A7 registers. Okay? And for those of you who started doing Lab 1, you might have noticed that instead of using X registers, we told you to use registers A0 to A7. And so these are a subset of our 32 registers. Specifically, they correspond to X10 to X17. But from now on, we're basically going to be using these names for our registers, not the X names for the most part. Okay? So we can have up to 8 arguments, and they would go in order in A0 through A7. So the procedure that's being called knows that its first argument can be found in A0. And if it has a second argument, its second argument can be found in A1, and so on, okay? And it's the responsibility of the caller who's calling this procedure to put those initial argument values into those registers. The next type of register is where we return our return value from our procedure. And here, once again, we use A registers, but we only have 2 available. Generally, our return value is always an A0. You do have the possibility of having 2 return values, in which case it would be an A1. All right, next is our RA register, which is the return address register. That happens to correspond to register X1. And now we have 2 other types of registers. We have a few registers which are called temporary registers, and a few registers which are called saved registers. So how do we use these registers? Specifically, the idea of a temporary register is that you don't care about its value moving forward. Okay, so you might use a temporary register in a situation where it's okay for the procedure that you're calling to overwrite that register. On the other hand, if it's important for you to have the value of a particular variable upon return from your procedure, then you would want to use an S register, because S registers, by convention, are guaranteed to always be returned with the same value as when you made your procedure call. Okay, so just a couple more, and we're going to stop in a minute. And so then we have our stack pointer happens to be X2, and these other ones you don't really need to focus on for the moment. And then we have X0, which we said is always 0. Okay, so the last thing that I want to say for today is just notice this right-hand column, which says whose responsibility it is to make sure that the register is saved. And so for the first 4 rows, it's the responsibility of the code that's calling the procedure to make sure that if it wants to access any of the A values or the RA value, it better save it before calling the procedure. The ones that are labeled callee is the responsibility of the procedure itself. So if it wants to, the procedure wants to make use of these saved registers, it's responsible for first saving it onto the stack and then restoring it upon completion, because it has a contractual obligation to make sure that those registers have the same value upon return from the procedure that they did when you entered. Okay? In tomorrow's recitation, we're going to start going a lot through these calling conventions and getting you guys comfortable with it. You'll only need this for lab 2. You do not need this for lab 1. All right, thanks everybody.